Hi everybody, welcome. We did sort of an introduction to cyclic stresses or fatigue in the last class. And now we're going to start to quantify that a little bit. So we'll define a lot of terms today, and we'll get a very deep dive into the stress life method for design against fatigue, and specifically kind of the order of operations. So what do you need to get started, and then how do you modify it to come up with kind of a final answer? Okay. And so the first thing we're going to do is just define some terminology. So if we have a load, let's say it's a stress, so that's on the y-axis, and it's a sinusoidal function like this. It's not symmetric exactly, but pretend it is. Then the deviation from 0 is going to be a stress amplitude. So there's going to be a mean. In this case, I've drawn the mean at 0. And then sigma A is the stress amplitude. And we can also describe kind of the magnitude of the fully reversing stress if we want, or the range of stress, let's say, which is equal to just the max minus the min. I talked already about the mean, so we can, if we don't know if the mean is non-zero, we can calculate that, right? But we can define the mean stress, sigma mean, right, as just the average of the min and max divide just the average of those two. So 1 plus the other divided by 2. We can calculate a stress ratio if we want. And so that would be called R. Okay? And R is just going to be the minimum stress divided by the maximum stress. And then if we want to, we can also take this ratio and apply it to these min and maxes with the stress amplitude in there as well. So we're going to call that capital A, which is the amplitude ratio. So that's going to be the stress amplitude sigma A divided by the mean stress sigma M, which I wrote mean before, but it's usually just sigma little m. And we could plug in the definition for the mean stress and the stress amplitude there and come up with 1 minus R, 1 plus R, right? So these are kind of the metrics we can use to describe this sinusoidal stress. This curve has two things that are important for SN curves. The first one is its constant amplitude. So across the curve, it goes up and down away from the mean, the same. And then it also has a 0 mean stress. We can also think about curves that might be experienced by machinery that have a 0 mean stress, but not a constant amplitude. Right, so stress, and this is time. I forgot to write that on the other one. Right, so we could have like this, right? So increasing amplitude, but same mean stress. We could also have different phases of this curve, same axes, stress and time, that have different mean stresses, right? So we could have some cyclic stresses like this, then back, then up and down, right? So this is what would happen maybe in machinery that has different loads over different times that's not determined by predictable mechanics, right? So for example, aircraft going through different airstreams, right? We can't predict the local sort of fluctuations in those airstreams, just how they generally change. So this might be a measurement where you have a segment here with a mean stress that's greater than 0. You could have a mean stress that's 0, or you could have regions down here where the mean stress is less than 0. So these are the different types of situations that could be experienced, and we'll talk about how to go from one to the next, at which point we might get to, after damage accumulation, talking about stress versus time and something like this, where then you have a loading event, then you have stresses up here, then it's unloaded again, or it's loaded to less than 0. And so this type of plot like that is given in the textbook in figure 7.6. And I thought the caption was unique. It says, a quasi-random stress time pattern that might be typical of an operational aircraft during any given mission. So I would assume that when the stress goes up, the aircraft is experiencing a lot of lift, and it's causing some particular, in this case, tensile stress, with a mean stress much above 0, and then some fluctuations, stress amplitude around that. And then when the mission is ending, the aircraft lands, the lift is no longer on that component, and it goes back. And so this, if this is for a typical mission, then you would add this up many, many times, and that's what the sort of life stress profile would be for a particular component. And so we'll talk about damage accumulation, and we're going to start with just fatigue and completely reversed constant amplitude loading. So this is all based on in the past, as I said, noticing that components that didn't appear to be stressed above their yield strength would all of a sudden fail, right? So maybe a crack initiation was missed, and then the crack propagated through, and then the component would fail in a catastrophic fashion. And so one researcher named R.R. Moore designed an experiment that was highly controlled in order to measure fatigue. And so it looked something like this. He took a specimen that was circular and had a thin section in the middle. Whoops. Something like that. So it's a cylindrical sample. And it would be mounted into 2 fixtures on the ends. All right. And it's symmetric, but I may not be able to draw the whole thing. Okay. All right, there, okay. So you put it in some fixtures, and then put some bearings on this thing so that it stays in place. So I'm going to draw those on top and bottom. Okay. And then there is this specimen in the middle that a force is applied to in some kind of way, and this could be a hanging weight with another bearing. It could be a side, displacement applied by something also with a bearing, but there's a side load here in the middle, and then this entire system is rotated. And so the rotation, if there's a side load on the specimen, the rotation causes a fully reversing constant amplitude experiment on every location around the circumference. So imagine you are a nanoscale person and you're sitting on the specimen. As if the load goes down like that, let's say you start on the back side here, right? So when you start, you're in compression. And then as the thing rotates around, you rotate down to the bottom. Now you're in tension. Now you go back to the top, you're in compression. And so that's how this sinusoidal curve is generated. Okay. So this is a rotating bending machine. And then after something like this is set up and working, then he changed the materials, he changed the surface finish, he changed heat treatments, he changed the metallic specimen in all kinds of ways in order to test those effects on the fatigue resistance of the component that's in there. So this is a rotating bending experiment. You can also have a bending machine, or what's also called a flat plate machine. So I'll draw that on the next slide, in which you take a flat plate, right? This is a side view. And you mount it into a fixture that's not going to move. So it's kind of clamped in. And then you put a driving clamp at the other end. All right, and this region that it occupies on the beam is very small compared to the length of the beam, so we can treat this as like a Bernoulli beam. And then this would be hooked up sort of like a connecting rod in an engine to some sort of rotating component like this, right? So this is a wheel. My connecting rod connects to it. As the wheel rotates, the connecting rod moves and causes the beam to bend up and down. Right? So there's a reciprocating motion, and it's fully reversing, right? And it, instead of having it be due to this rotation, we have a flat specimen, and it just flips up and down like a diving board. This one is a little bit more unique because you can change the mean stress. Right. So if you just have it as a fully reversing stress like that, that's fine. If you move the center point of this drive upward or downward, then you can change the mean stress. Right? You can't, so you could move it up to something like that, right? And then do some experiments that way. If you had two identical specimens, you could slowly change the mean stress and look what happens there. And then there are other sort of more complicated ones. For example, if you want to have a specimen subjected to a fully tensile, whoops, that's really asymmetric. But if you wanted to have it subjected to a fully tensile load, you could do that. Change the mean stress through a series of pivots and drives. Like these things are fairly readily set up. So the one that we're going to use as a reference is the SN diagram, which I hinted to before. So that's from that RR Moore bending rotating test. And it's used to create a set of failure points on many different samples. And that's going to be called the SN diagram, or the Voller curve, right? And I will draw it in detail on the next page. And this is the most basic of design tools for fatigue, and we're going to base everything else we do off of these kinds of diagrams. Okay? So N is the number of cycles that have been experienced at a particular location on a component. And then S is the stress amplitude that is experienced. So this is not the fully reversing stress range. This is just the amplitude. And so what happens is, for a given material, we usually start this at about 10 to the third on the x-axis. And kind of anything below 10 to the fourth cycles, we said was low cycle fatigue. So we're really going to focus on everything up to like 10 to the 6, 10 to the 7. 10 to the 6 is always a million. And then you can get out to like billions of cycles. And so let's say we had a specimen and we put it at some particular stress amplitude, and we just started cycling that thing in like the RR Moore bending fatigue. We would come up with a distribution of, let's say we had like 100 samples and we did the same test, the same stress amplitude on all of them. We would come up with a distribution that would be clustered around some mean and then would have like a tail. You know, I'm drawing it sort of idealized, but it would have a tail like that. Okay. And so if we wanted to look at only that experiment and say, what kind of a distribution is that? This is normally modeled as just a normal distribution or a Gaussian distribution, where you could say that there's a number of specimens on the y-axis, right, and the cycles that they failed at. And so if you did like made a bar plot or something, right, you could model that as a normal distribution. And so that's one set of experiments at one condition for a bunch of samples. And so we find that there's a distribution because of material defects, changes in the surface finish, and small differences between the samples that are very hard to control for. And this could even be small changes in like the heat treatment of the material. So this is not something that is readily identifiable, right? People could try to hunt it down, right, and try to make the same sort of exactly the same materials, but it's very hard to do. And so what happens is this same thing is done at, let's say, a second level of stress. Right up here, and then we'll do it all the way up till we are, let's say, I don't know, 0.8 times the ultimate strength, right? And then we'll get sort of a tighter distribution that's right around 10 to the 3, 10 to the 4. And then as we go out at lower stress levels, the data starts to spread out even further, like this. Sorry, my X's are getting messy. All right, and we go further and further, and then we really don't get many data points at some low stress amplitude. And then so how these SN curves are created is they take the center of each distribution and connect it with a smooth line. All right, so we do something like that. That's how these SN curves are created. So if you look up like an SN curve for a particular material that you are interested in, this is where those come from. So there is some scatter in just creating the curves in the first place. And this is good. This is where you would you would use this curve in an undergraduate class, and you would apply a bunch of factors to it. And I'll just review those briefly so that we're all starting from the same place. But if you want to go one step further, and this is kind of what I talked about, there's this window of failure. You can put a series of curves on here that have to do with reliability, right? So if you remember from statistics class, right, there were often problems like I've tested 100 things at exactly the same conditions, and I got a distribution that was like a normal distribution. If I subsequently measure one additional measurement, what is the probability that it would fall within X domain? Like within 1 standard deviation, within 2 standard deviations, things like that. And so those reliabilities can be used to generate a family of curves like this. So I'm just sketching on this plot that I've already made. And so if we look at the center one that we drew, that would have a reliability, we'll call it R, and that's defined as a reliability of of half. 50% reliability, not 1, half. Because if we were to subsequently, so we made 100 measurements at all these conditions, and if we made one more, we'd have 50% confidence that it would fall sort of close to that line there. And then the further we get away from that, our reliability drops off, right? So for the next line, we could say that our reliability is like 0.1, right? Or that would be 10%. And then we could go, hang on a second, these are, let me make sure I write this correctly. Nope, I didn't write it correctly. Let me start and go back. It's just the R's. The curves are right, it's fine. Okay, so for that center curve, that's the one we know the best, right? So that reliability is going to be approach 1. because that's at the center of the distribution. And then as we go out from there, then we drop off in reliability. Whoops, that's not even my middle curve. Good night. All right, that was the initial curve that I drew. So then as we go out from there, the reliability will drop off some. So then we would have like 90% reliability, right? And then 80%, and it would move out like that. And so what we want in a design situation is to start with the highest reliability curve, and then we will apply a factor to say how reliable we want our design result to be. There are two classes of materials that were tested, and there's one very big difference between them. So we'll have our stress, which is a stress amplitude. And so for ferrous alloys and titanium, there appears to be, ferrous alloys and titanium, an identifiable asymptote in this plot where it really just goes straight out parallel to the x-axis. So it reaches what's considered to be the fatigue limit. So when we talk about steel alloys, and titanium, you can say there is a fatigue limit. This is also called the endurance limit. And if stress amplitudes below this magnitude are applied, it's expected to have infinite life, right? Because it never hits that SN curve. However, for non-ferrous alloys, so I'll draw another curve like this. It never hits that asymptotic section. So the curves don't do that. They just continue to decrease. I mean, they have a small slope there, but they just continue to decrease. And so we cannot say that non-ferrous alloys have a fatigue limit. So no fatigue limit. However, we can say they have a fatigue strength at some number of cycles. An example of a non-ferrous alloy would be aluminum, right? Bronze, brass, a lot of things like that are made of copper and things like that, okay? So they have no iron. That's what non-ferrous means. And so this will come into play later on when we start manipulating and looking at effects on some of these curves. We really have to take care whether we're talking about non-ferrous alloys or ferrous alloys. Okay, so this is fine, right? So you understand how the experiments work. Somebody could do with the RR more, the bending thing, except we need a way to sort of estimate this, right? There's kind of an infinite number of materials that we could identify. And so if we were starting from just, I've got this particular grade of steel, how can I start my problem, at least to get going and estimate my endurance limit, estimate sort of this SN curve. And so what has been found is a correlation between tensile strength, this is the ultimate strength, so SUT, and the endurance limit, which we are going to call SE, and in this case, I'm going to call it prime. Okay, so SE prime just means kind of like from the rotating bending tester, right? This ideal endurance limit. And so if 3 sets of experiments were done, so carbon steels, right, those are very common, alloy steels, and wrought iron, then these are all ferrous materials. So they should have an endurance limit. So when these were tested, came out with 3 sets of data. Wrought irons don't do very well, okay? So if you know anything about wrought iron, it's very hard and it's not very uniform. So something happened like this, right? Where there's a bunch of clustered data close to the origin. And so the ultimate tensile strength is kind of in the range of 40 kpsi, and the endurance limit is kind of about 30 kpsi. Okay, so it's kind of a one-to-one. Hard to say that there's any trend really based on that. So the wrought iron, I'll just put a plus next to it. Then you can get a much higher ultimate tensile strength from something like an alloy steel. Okay, so I'm going to do that as, I don't know, like a box, something like that. So if we draw that on there, we get a lot more data points. Right, and I'm just going to draw a bunch, and I'm going to reduce the number from what the data actually is. I'm going to kind of draw it. Okay. So it's still scattered, but now you can start to see there's like a trend, right? We could draw a line through that, so that can be helpful. And then you can also do carbon steels. So I'm going to draw those as like a circle. Here's my legend. Okay. So these are just sets of experiments. Okay. So we draw something like that. We find that the carbon steels and the alloy steels, they kind of overlap. And so we can draw sort of a dashed line through all of them, right? And depending on I didn't draw the data points exactly great here. But if we draw a dashed line through all of them, we kind of find a correlation of about a half. So that would be the slope of that line, right? So out at the top here, this might be like 260 kpsi. And then over here at the highest would be, if it's about a half, 130 kpsi. We can draw different lines that represent different slopes, right? So we could do like a 0.6 and a 0.4. And those are not bad, estimates, especially for if these tests are done and you find that they fall sort of along one of those extremes. That's fine. But the rule of thumb that we're going to use is that the endurance limit is going to be half of the ultimate tensile strength. So as long as a specimen has had some kind of a set of tensile tests, then you can estimate its endurance limit. This holds for, let's say, materials that most carbon steels and alloy steels. Okay. You will notice, though, that there's a section of this plot that kind of went down at the higher levels, right? So if I take a red pen and sort of point an arrow to it, there's some data there that starts to not follow those trends. And so those materials have very high tensile strength. So there's kind of a rule where if we get up to like 200 kpsi in tensile strength, we say that there's a cutoff, right? So once we get up to a material here, it no longer follows that 0.5. So we kind of say there's a cutoff, and then we just say we estimate that endurance limit at 100 kpsi. Right. So for really high strength materials, we sort of just clip it there. Anything above that, just assign it 100 kpsi. Okay. So this is good. This gives us a starting point. And so if this gives us a starting point, and we had another data point we could point to, we could sort of draw up an SN curve without having all the experimental data, and at least get some estimate of the slopes of it without having to have that particular material tested. So I'm going to draw another SN curve here. Okay, and we'll have like, they keep calling it S, but it's really like sigma A. Okay, so let's say we have some material, and we want to just sort of draw a mock SN curve so we can start making some estimations. We really don't have a lot of data before 10 to the third cycles, so we're really just going to start there. And then we're going to go out and assume that infinite life means 10 to the 6 cycles, 1,000,000 cycles. Okay. So we can draw what we know already, which is our endurance limit, SE prime, which is going to be half of the ultimate tensile strength. Right? We can just look that up. That starts here and goes that way. Right? So that's the first thing. Okay. And then we can look at 10 to the third, and we can draw something here as an estimate, which is also from empirical data, which is we get to a value that's about 0.8 times the ultimate tensile strength right here at 10 to the third cycles. And then it's going to have some sort of line going this way. We don't know what's happening there. So now we have 2 points, and this is a log-log scale. So both of these axes are logs instead of a linear scale. And so if we draw a straight line between those two, this is kind of our mock-up SN curve. And we can say that the stress amplitude is some constant times the number of cycles to some power. So a straight line on a log-log plot has a power law. So we can apply a power law to fit directly to that. So we know these two locations. So we sort of have 2 points on this curve. Our first point is the x-axis is 10 to the third, and the corresponding point is 0.8 times SUT. And then we have the other point, 10 to the 6, and 0.5 SUT. So if we have 2 points, and we have an equation with 2 unknowns, A and B, then we can solve for A and B. Yes? First point is right here, 10 to the third. And then I sort of just wrote that there's a convention that this is around 0.8 times the ultimate tensile strength. Yeah. Yep. It can change based on what is the ultimate tensile strength of the material, but as a conservative number, we can just start with that. It can vary, actually. I think there's a chart. It can vary between, I think, 0.78 to 0.98. So I chose something relatively conservative. Good question. So if we have 2 points on our line, and 1 equation describing that line, right? And we can take the log of both sides and things. We can solve for these constants. So A is going to be kind of 0.8 SUT, parentheses, squared, divided by SE, which is the 0.5 SUT, and and B is equal to minus 1/3 times the log of 0.8 SUT divided by 0.5 SUT. So you could solve for A and B, and then you'd have an equation for this part of the curve, which is the important part. Right, so I'm going to highlight it here in red, which is the important part if you don't have infinite life. And so this is a starting point. Yes, question?
How come the SUTs don't cancel and become constant?
They do cancel, yeah. So in the undergraduate textbook where this approximation comes from, they leave this as a factor, this 0.8, and so they didn't simplify it down. So when I brought it into this lecture, I just wrote it out like that, but it does cancel out, yeah. So it cancels out here, and then this squared would cancel out, at least the SUT part, right? Yeah, it does. Good question. So then so the general procedure is if you don't have the SN curves, but you know the ultimate tensile strength, you sort of create a fatigue curve like this. And then once you get your, once you calculate what your SE is, you want to know sort of where you are on this curve. Sorry, let me say that a little bit more clearly. Now you have this curve, and you want to modify it for the specific situation the component is in, right? So this is only based on material properties and empirical findings like these factors and observations of ferrous metals, right? So now we have maybe something that's in different types of loading, right? Or different temperatures, it's a large component, it's a small component. And so this is what we teach in our undergrad class, which is that we have our actual endurance limit for our part. So that's SE prime. Sorry, that's SE. Our part is going to be this sort of endurance limit from an ideal rotary test times a bunch of factors, which are called Marin factors, after the person who put them together. And what the Marin factors do is they collect a ton of information and kind of distill it down to something that might be useful for prediction. Okay? And so there are multiple factors. There are 5, and they are listed just sort of A, B, C, D, E. So there's a surface factor. And because these are factors, they're all multiplied together. So we do Ka times the other factors. So Kb is a size factor. Kc is a load factor. Kd is a temperature factor. You don't have to memorize these, by the way. Ke is a reliability. Factor. And then we just multiply all these together, and they modify the optimal endurance limit from the RR Moore tester to get a value that's for our part. And they don't just modify it, they reduce it. So in an ideal situation, all of these Marin factors would equal 1, and our part is this RR, more perfect specimen. So the one from that tester and our part would be equal. But in reality, we have all of these different things that change between that ideal test and our test. So all of these factors are less than 1. And so what they do is they reduce the endurance limit. Okay. And some of them can reduce the endurance limit significantly. So how you would incorporate this is like, let's say you have a design part, you know the loading. Well, then you have a material and you want to see if the stress you're applying is going to cause a fatigue failure. So first, you would find your ultimate tensile strength from some kind of materials testing database. You would calculate SE prime from that, and you could recreate your fatigue curve if you wanted to. You don't have to. But if you want to see now if your part's going to be above or below this endurance limit, then you have to apply these factors. Okay. And then at the end, you are going to have a sort of an endurance limit that you can compare with the stress that is on your part. Okay. And all of these factors are sort of a simple way to try and give some predictive ability, but they all come from long sets of fatigue experiments. Okay, so when we're teaching this in undergrad, we kind of say, these are the factors, you look them up, you multiply times 0.5 or whatever, and then you move on, and we don't spend a lot of time talking about where they come from. But I want to make sure and hit that just a little bit today. So this is in chapter 7 of the book, and it talks about factors that affect these SNP curves. So SNP is what they call the SN curves because they add in a reliability factor. So they call them SNP. And a lot of the factors, people will try to run a controlled series of experiments. Sometimes they are quantitative and sometimes they're more qualitative. And we just try to assign a factor that generally captures the behavior for some kind of predictive ability. Okay. So we already talked, so now I'm just going to write down a few of the ways or like factors that affect SNP curves, which in turn sort of like, or by definition, affect the endurance limit. We talked about one already. I talked about material composition, ferrous versus non-ferrous. Okay. Another one is grain size. Okay. If you've taken an advanced manufacturing course here, you may have talked about Hall-Petch behavior. This is two names combined, Hall-Petch. And Hall-Petch behavior says that the yield stress of a metal is proportional to 1 divided by the square root of the diameter of the grains, the average diameter of the grains. So I'll write that here, average grain diameter. And there's some other constants in there, but it's proportional. So as the grain size gets smaller, the grains get more refined, and there is less ability for things to yield, so it increases the yield strength. Okay? The exact Hall-Petch behavior cannot be applied to fatigue strength. The effect is diminished, but the effect is still there. So the book gives an example of a fine-grained material. So fine-grained. And they give it in terms of a grain density. So they say it's like 82,000 grains per millimeter cubed. Okay. And then they compare that with a coarse-grained material, which only has 4 grains per millimeter cubed. So that's pretty extreme as far as crystallinity goes. But the endurance limit for this one, if it's an 18, they give it as 18S aluminum alloy, and whoops, I used the word endurance limit. The fatigue strength at 10 to the 8 cycles. So at 10 to the 8 cycles, the fatigue strength of the fine-grained one is something like 28 kpsi, and the coarse-grained one at 10 to the 8th, if we compare that, is at about, nope, I lied, that should be 18. It's just a number in the book. And then this one is at about 15. So it's not as much of an effect, right, as Hall-Petch behavior. There's no like specific strong inverse relationship. but the smaller the grains, the higher the fatigue strength generally. Heat treatment is another one. If you've taken a materials class in which you had to draw the phase diagram for steel and then talk about different methods of melting and quenching and following paths on that phase diagram, you would remember that there are different phases of steel, like the alpha and the gamma, and they had different names like martensite, right? And things like that. So the heat treatments, especially of ferrous alloys, can change the fatigue strength. And so they give an example in the book of a steel. I don't think I wrote down what kind of steel, but it's a steel. And if it is heated up in a furnace to 1500, I think it's 1500 F, I don't exactly remember, and then it is just left in the oven to cool. Right? There's no quenching, it's just a very slow cooling, then it's going to have a lower endurance limit than if it's quenched, right? So if they take it out and it's quenched when it's about 700 degrees, they take it out, quench it, then it's going to have a better endurance limit, right? And that's all due to the different phases and the sizes and the concentrations that happen during these processes. Okay, this is actually not. Yeah, that's fine. Welding and fastening. So in an ideal world, we could create monolithic parts, right? We can dream up a part like an engine casing or something, and then we make it monolithic. There's nothing that has to be welded or fastened, but in the real world, we often have to weld or fasten things together because we don't have infinity money. And so the welds will create, right, local heat affected zones, which can act as locations that have a lower fatigue strength. And if we also try to put things together with rivets or bolts or something like that, those are obviously not part of a monolithic structure. And so the properties of these and the way that they're assembled has to be considered in the fatigue failure of the overall part. The next one is geometric discontinuities. I think they forgot to do my 5-minute warning. It's already 2:44. And so the greater the extent of the discontinuity, for example, a sharp notch versus a broad radius. So a greater extent of a geometric discontinuity means a lower endurance limit. Okay. And then the last one I'm going to mention, because I think we're very tight on time, is the surface conditions. So let's say you had a part and you wanted to put a coating on it. You wanted to plate it with nickel or chromium so that you could help prevent corrosion. That is a good idea, except some of those surface treatments create then a surface where there's different material properties and maybe a discontinuity in material properties near that coating, which can be an opportunity for fatigue crack nucleation. So there are some surface conditions that have a large effect. So any kind of cladding or other kind of thick coatings and then plating procedures can have a really big change on the endurance limit. Small changes occur for thinner coatings, so like anodized coatings. Right. In that case, the endurance limit is not changed very much. Or if you plate it with something that is a pure metal, such as zinc or cadmium, except cadmium is not as environmentally acceptable. So I think I'm going to end there, and we'll pick back up with how to account for some of these changes, and then move on to non-zero mean stress considerations. So thanks, everybody.